Hello and welcome to this EE328 lecture video on discrete time convolution. This lecture assumes that you have seen the introductory lecture on discrete time convolution as well as been exposed to some of the properties of convolution, because we're going to use those topics to move on into the field of more advanced convolutions. So in particular, what we haven't talked about so far is when we convolve periodic signals, or what is involved when one would convolve periodic signals. And this is relevant because it's often very important, especially if you remember how important sines and cosines were in LTI systems in continuous time. We're going to want to know what LTI systems in discrete time do to sines and cosines. But in general, if you have an LTI system and apply a periodic input to it, you're guaranteed that the output will also be periodic with the same period. So for example, the easiest example to do is a finite impulse response filter. And let's apply, this statement is true for arbitrary periodic inputs, but let's put in this cosine that has a rational frequency, which of course means that this is a discrete time cosine that is periodic. If we're going to convolve a finite length signal with an infinite length signal, then the best approach is the analytical approach. So y of n is the linear convolution of x of n with the impulse response h of n. And this is also the same as h of n convolved with x of n. And I'm going to prefer that second form. So this is again the summation over all possible k's of the first signal, h of k, times the second signal evaluated at n minus k. Now I like doing it this way because the h signal is finite, and so this infinite sum actually reduces to a finite sum. This is the same as k running from 0 to 1, because there's only 0 and 1 time instances in h of k times x times n minus k. And so now the utility of using the sigma notation is kind of used up, so we can just write this as h of 0 times x of n plus h of 1 times x of n minus 1. Okay, and this makes sense, I hope, because every impulse lasts in the system for 2 time instants. So therefore, every pulse along the x signal is going to last in the system for 2 time instances. Okay, so now we can plug in our form for x, and we get something like h of 0 is 1 times cosine of 2 pi big F times n. And then h of 1 we just picked to be 2 times cosine of 2 pi times f times n minus 1. Now this is simply a cosine added to an amplitude scaled and phase shifted cosine. So I hope you see that the answer will be a cosine with the same frequency. So to make that explicit, this is cosine of 2 pi big F times n plus twice cosine 2 pi fn. So there's the same frequency and then minus a phase shift. And the phase shift is a big F fraction of 2 pi. Okay, so this is going to be an amplitude scaled and phase shifted cosine at frequency f, which if we started with an n period will end up with an n period. Okay. And that is true for any finite length of impulse response. So I just picked a length 2 here, but you could keep doing this and you would get more sums of cosines together. In the second example, it's a little less obvious, but even if you have an infinite impulse response, we can still show that the output due to a periodic input will be periodic. And so the choice here is we're going to let h of n be any arbitrary infinite duration signal. And x of n, rather than a cosine, I'm going to pick a complex exponential, which is still n periodic if capital F is rational. Okay, so let's set up the convolution, which is going to be the sum, k running from negative infinity to infinity, of h of k, again I'm swapping the order of convolution here, times x of n minus k. Now I don't have a form for h of k, so all the work has to be done here in the x signal. So this is going to be the sum over all k's. And what happens when we time delay a complex exponential like this? Well, we get e to the j 2 pi times f times n minus k. But if I have a difference up here in the exponent, then that's the same as multiplying exponentials. And so one of those exponentials is going to be a function of n only with no k's, so I'm going to pull that out in front. So we get e to the j 2 pi f times n times this summation, e to the minus j 2 pi f times k times h of k. K running over all the integers. And so I want to point something out here. We started with this as our input, and that actually pops up here again. So this is the input signal as a function of n. So then the question becomes, what is this? Well, let's establish what it's not. It's not a function of n. This is not a time signal. There are no little n's in this summation. So if it's not a function of n, is it a function of k? Well, no, not really, because once you do the summation over k, remember it's like a dummy variable, the k's are going to go away. So really, the only variable left here is f. This is a function of f, which means that for a fixed f, right, if you pick f equals 0.1345, then what are we going to get out of this system but this function evaluated at 0.1345 times the input. And since the input was n periodic, that means the output will be n periodic. So this is actually just not any old function of f. It actually gets a name. This is called the discrete-time Fourier transform of h evaluated at capital F. But we will get into the details of that in a week or two. But for now, what's more important is to see that if I put in this complex exponential, I get out that same complex exponential subject to perhaps a scaling and a time shift based on what the function of f works out to be. So we've so far talked about convolving periodic with finite, periodic with infinite but not repeating, and now the question is what happens when you convolve a periodic signal with a periodic signal? And the answer is nothing, or infinite if you like. If you have a periodic signal, you convolve with a periodic signal, unless you do any kind of averaging, the result will be infinite at all time values. So, right, so if you have this sum of some periodic function of k times some other periodic function of k, there's going to be no simplification on this sum. It's just going to run forever and ever, and you're going to get potentially non-zero elements everywhere along here, and you're going to add up an infinite number of those, and so the result of this summation rarely makes sense. So strictly speaking, we say it's not going to be defined. This is not a huge loss because the number of systems whose impulse response is truly periodic is not very interesting. Right, so most of our systems are causal, or at least can be shifted to become causal. And if you're a causal signal, then you can't be periodic because you are not active for times less than 0. So even if your system is causal and, say, marginally stable, so your impulse response oscillates, so impulse response looks something like this. Then you can take the DTFT of this, and you can use our method from the last slide to analyze what the output of this system will be due to a periodic input. But I want to emphasize that this is not a periodic signal. even though it oscillates in positive time, precisely because it doesn't oscillate in negative time. That's not to say that the notion of convolving two periodic signals isn't useful. What I do mean is that taking the linear convolution of two periodic signals is fraught, I'll say that. And so what we would like to do is maybe define a new notion of convolution that allows us to convolve periodic things. And so you will see this symbol. Sometimes it's the asterisk with the circle, sometimes it's the star with the circle. But either way, this is called, in some books, periodic convolution, or in other books, it is circular convolution. I'm going to prefer this notion of this term of circular convolution, but you should know that it's called both things. And I want to emphasize that it is not the linear convolution of two periodic signals, and that's actually why I don't prefer this first phrase. It's because I think it muddies the waters when you talk about the periodic convolution of two signals. I want to stress that this is not the same as the linear convolution of two periodic signals. Okay, so we have to redefine what we mean by circular convolution or periodic convolution. And the essence of what we mean when we say this is that you are going to take one period. So say this is one period of f, of the signal f, which is periodic. So because we are assuming that they are both n periodic, this has length n. And then the same here. This is one period of g, which is also length n. And so now we have to modify this notation a little bit. When I talk about shifting and flipping in circular convolution, this has to mean a circular shift instead of a linear shift. So in particular, what do I mean by circular shift? If I have a sequence of numbers 0, 1, 2, 3, then a circular shift, a right circular shift, just means everything moves to the right, and then off the end, moving to the right from the end actually moves you back to the beginning. So this would be a right circular shift if we end up with 3 at the beginning, then 0, then 1, then 2. Okay, and so that's what I mean here when I talk about a circular shift of n minus k. This is g0, so one period of g, as a function of k, flipped around, and then shifted by n, circularly shifted by n units. Okay, so let's see that in action, actually. There are actually several ways to compute the circular convolution of two n periodic signals, but they all revolve around reducing both signals to just one period. And so that's what I've done here, and I've denoted them just one period segment of f and g as, say, 102 and 123. And so the first way that I want to show you how to compute the circular convolution between these two signals is actually a bridge from linear convolution. So what we're going to do is we're going to linearly convolve just these two one period segments of these two signals, and then after the fact we're going to wrap around the result to make it 3 periodic. Why 3? Because both of these are n equals 3 periodic. Okay, so in fact, let's use this opportunity to practice our sliding strip method. So let's write the k row as 0, 1, 2, and f of k will be 1, 0, 2, and g of minus k would be 1, and then I'm going to right to left, 1, 2, 3. So here is f of k. Here is g of 0 minus k. And let's set up the columns. And so this will be our output, y of n. Okay, so at n equals 0, we get 1 times 1 is 1. And then we can shift this over, so we get 1, 2, 3. So this is g naught of 1 minus k. So this will go in the n equals 1 box down here, which is, we're looking at this times 2, 1 times 2, 0 times 1, so it's 2. And then we'll shift again, so 1, 2, 3, right to left. And so now we're looking at 3 plus 2 is 5. And shift again, 1, 2, 3, right to left. And so now we're looking at 0 times 3 plus 2 times 2 is 4. And one more time, 1, 2, 3. 2 times 3 gets us 6. Okay, so the trick here is that by convolving these two length 3 segments, I get a length 5 segment. And what is not obvious is that I'm now going to append a 0. But remember that this is a finite length segment, and so appending a 0 to that signal does nothing. And so what I'm going to do now is I'm going to save the first big N results, and I'm going to chop off the second big N results and move them down here. So I get 4, 6, 0. And so my final answer, or one period of the result, is going to be the sum of these two rows now. So I get 5 and 8 and 5. Okay, so the way to write this would be that the circular convolution between 1, 0, 2 and 1, 2, 3 is simply 5, 8, 5. Okay, and I want to drive home that this is not true if I had not put a little circle around that star, right? If I have just linear convolution, I would get this answer. But to compute the circular convolution, you can take the linear convolution and then wrap the end or the extra bit back around. And to show you why that's true, let's actually go after the second method. And here I'm going to use the circular shift method. So I'm again going to set up 4, 3, 2, 1. And here's f0 of k and g0 of minus k. So g0 of minus k would look like 1, minus 1, 2, minus 2. But what I'm going to do is I'm going to circularly shift these back around. So the minus 2 comes here, the positive 2 comes there, and the minus 1 comes there. Okay, so now this is g of minus k with a circular shift applied to it. This is what I'm looking at for my convolution now. Let's draw a big old table here. And for every increment going around here, we are going to write the pairwise product, the sum of the pairwise products in the next available box down here. Okay, so pairwise product looks like 4 times 1 is 4, that's minus 6, so plus 4 is 8 minus 6, that's 2, and then minus 1 gets me 1. And now I'm going to proceed with a circular shift on G0. So it would normally just go 1, minus 2, 2, and the minus 1 would go out here, but if we're doing circular shift, then the minus 1 comes back around there. Okay, so now I'm doing pairwise product with the top row and the bottom row. So I get minus 4 plus 3 is minus 1, minus 4 is minus 5, plus 2 is minus 3. Again, let's shift. So the easy, for me to visualize, it's going to the right here. So do that again, we get 1, minus 2, and then the 2 would go on the end, but I put it over here, and now the minus 1 can get shifted there. Okay, so now again, pairwise from the top row and the bottom row. So I get 4 times 2 is 8, minus 3 is 5, plus 2 is 7, minus 2 is 5. One more circular shift, so everything moves to the right, and the right thing moves back around. Okay, one more pairwise product, so minus 8 and 6 is minus 2, and minus 2 is minus 4, and 1 is minus 3. So in here, because we're doing circular shift every time, we don't have to, there's no extra bits to wrap around, and so this actually is your final answer. That F naught, or F circularly convolved with G gets you the sequence, the periodic sequence 1, minus 3, 5, minus 3, the periodic extension of that sequence. So the third method, and the method that I actually prefer to visualize when doing this, is it's not officially called clockwork, but it reminds me a lot of clock arithmetic. And so I'm going to use the same example that we just did, that we know the result from, and show you how this works. So I'm first going to draw a circle, and in the inner, I'm going to write f0 of k. So let's put 4, 3, 2, 1. So this is k increasing, and this is f0 of 0. And on the outside, so on the inside we had f, on the outside I'm going to write g. And let's do, because we have to flip g around because it's a reversal, I'm going to actually write g of negative k in the opposite direction. So that's 1, minus 1, 2, minus 2. Okay, so this is on the outside g of minus k. And so what we're going to do is we're going to look at pairwise products around the clock. So y of n, and we'll just fill in the gaps here. So this is now 4 times 1, and then minus 6, and then plus 4, and then minus 1, and that gets you 1. And so now we will rotate, which is the same as circularly shifting the outer set of numbers. And so the way I like to do it is if I write my inner sequence in clockwise, then I have to write my outer sequence counterclockwise, but then I'll rotate my outer sequence clockwise. Okay, so the writing it counterclockwise accomplishes the time reversal, and the spinning it clockwise achieves the time shift as n goes forward. Okay, so let's go with a different color here. So the 1 comes over here, the minus 2 comes over here, the 2 comes over here, and the 1, the minus 1 comes over here. All right, so then the red result is minus 1 times 4, so minus 4 plus 1 times 3 is minus 1, minus 4 again is minus 5, and then plus 2 we get minus 3. Let's see if I can get another color. Let's do orange now. So now we're going to circularly shift again, and so now the 1 comes here, the minus 2 goes here, the positive 2 goes up here, and the negative 1 comes around here. This is easier if you actually have like a disk that you can spin around. You don't have to keep crossing or erasing and rewriting the numbers. But if you do this pairwise product, so I'm looking at 2 times 4 is 8, minus 3 is 5, plus 2 is 7, minus 2 is 5 again. So we get back to here, and let's see if we can go one further. So now this becomes the 2, this becomes the minus 1, this becomes a plus 1, and this becomes the minus 2. And so we're looking again at, so minus 2 times 4 is minus 8, plus 6 is minus 2, minus 2 is minus 4, plus 1 is negative 3. And so we actually get the same answer that we got before. And for me, this is a little bit easier circling around. It's a little easier than this if we actually have paper that you can rotate around. But the concept is the same. And this actually drives home what a circular shift is instead of a linear shift. Okay, lastly, and probably the more practical way to do all of this is with what's called a circulant matrix. And so if I want to write F circularly convolved with G, then one way to do this, method 4, I suppose. One way to do this is to construct a circulant matrix out of the F segment. And so let's start by writing F vertically in the first column, 4, 3, 2, 1. And then it's called a circulant matrix because you're doing a circulant shift from column to column. So in the second column, 4, 3, 2, the 1 would drop off the bottom, but it comes around the top. In the next column, we get 4, 3, 2 drops off, then 2, and then 1 comes back down. And again, we're doing 2, 1, 4. The 3 would drop off, and now it comes up here. So this is the circulant matrix formed from the vector F. And in order to find this circular convolution, you can then just transform G if you write it out here. So 1 minus 1, 2 minus 2. And this is just your typical matrix transformation of a vector. And so if you do this matrix transformation, and this is why I say it's a more practical approach, is because this is a more computable way, or a way to instruct a computer to do this. You would actually get the same answer that we have been getting the whole time. Something like 1 minus 3, 5 minus 3. Okay, so that's 4 different ways for you to visualize how to accomplish what's called a circular convolution. And I want to emphasize one more time that a circular convolution is not the same as a linear convolution. In particular, you know, because of the lengths, right? If you are circularly convolving 2 signals, they have to be the same length. You can, of course, zero pad to bring them up to be the same length, but the real gotcha is that the result of a circular convolution, so F circularly convolved with G, the length of this is the length of F, which is the length of G. And that is not true for linear convolution. The last topic that I want to talk about for convolution goes back to linear convolution, and we're going to talk about correlations, which is just simply a measure of similarity after a time shift. So we say the autocorrelation of x, of course auto means with itself, so correlating x with itself, is simply a measure of how similar x is to a shifted version of x. And so this is very similar to linear convolution, except here. Right? If this were linear convolution, this would actually be n minus k. But in correlation, what we want to measure is a shift in x, not a flip and shift in x. Okay, but we can write this as a convolution if we pre-flip x, one of the x's anyway. So we know that xn star hn, or a second signal here, you would write this argument as n minus k, but if there's an extra negative in this argument, then you get actually k minus n, which is how the correlation is defined. Okay, so there's a couple things to note here, is that this is a function of n and not k. So in particular, if I evaluate rxx at 0, then we get the sum over all k's of x of k, and everywhere I see an n, I'll replace it with 0 times x of k, which looks like the sum of x of k squared, which is actually the energy in x, the signal x. So you can always recover the energy of a signal if you evaluate its autocorrelation at time equals 0. So the other salient feature of the autocorrelation function, and the one that we use the most, is that this value, this rxx of 0, is actually the maximum value over all values of n. And I hope that makes sense, that if we're measuring the similarity of a signal to a shifted version of itself, a signal can never be more similar than it is to itself when it's unshifted. And so we use this actually to measure when we have, say we know what signal we sent, and we have a received version, and we're trying to find where the known signal is within the unknown signal. And so that, at its heart, is actually a cross correlation, which is simply the measure of a similarity between x and a shifted version of y. And so this is kind of what I was talking about, is we can talk about having a known signal that we're looking for, and then it's somewhere, so the known is somewhere in here. We just don't know where. And so the application for this might be something like if you have a pulse, like a sonar pulse, and you were to send that into either the ocean or into the ground, and you would get an echo back from the nearest, largest thing in the ground, but you wouldn't actually know how long it would take to come back. And the other feature that I should not fail to mention is that often what you're going to get back is a bunch of noise. Okay, so this is a little quick demo that I coded up. And so the pulse that I'd like to send is this cosine over, I don't know, 4 or 5 periods of the cosine. And then if I send that cosine out and wait for it to come back, so I've waited much longer than the original cosine took. And the question is, what is d? Right. So in the sonar example, it would be how far is the pipe or the buried treasure, or if you're in a submarine, it would be how far is the sea floor from where you're emitting this noise. And so the idea is if you have a measure of the time it takes for your signal to go out and bounce back, then if you divide that time in half and then use the speed of sound or the speed of the wave in the medium that you're floating in, then you can derive a distance estimate. So what I've done is I have buried it in some pretty noisy signals here. So I don't know if you can try and pick out, but somewhere in this forest there is this signal. I just added it to a bunch of random samples. And so I think it's really impossible for me to tell exactly where. There might be something kind of recognizable there, but not quite sure. That same kind of stuff happens over here as well, so it's kind of ambiguous. But the cool thing is that when you pass y through a cross-correlator with x, it actually becomes quite evident that around about here and around about here, which are at roughly the same sample, we have a maximum, which tells us that the x signal occurs in this bin of samples here. So if we knew the speed of sound in saltwater, then we could derive the distance from the submarine to the seafloor using this method. Thanks for listening. I'll see you in class.